Hello, this is Mr. Deulis, and I'm going to go through a physics problem with you on circular motion, and we're going to be using some Newton's laws here as well. The problem is a 1,200 kilogram car rounds a curve of radius 67 meters banked at an angle of 12 degrees. If the car is traveling at 95 kilometers per hour, will a friction force be required? If so, how much and in what direction? So you can see my beautiful little drawing here where I've got the car rounding the curve, and we're looking at it from the side, and if we were looking at it from the top, it would be moving along the tangent. Here I've gone ahead and I've saved some time and written out all the variables. We have a mass that's 1,200 kilograms, the radius is 67 meters, theta is 12 degrees, velocity is 95 kilometers per hour, but converting that from kilometers per hour to meters per second, we have 1 hour 3,600 seconds, so the hours canceled out. And then we have 1 kilometer is 1,000 meters, so the kilometers then canceled out, and that gets us to 26.39 meters per second. So you can keep that in mind for a couple of minutes as we work. All right, so now that we've got that, I'm going to shrink that down a bit so that I can kind of move it off to the side and get it out of the way. What I've also done to save some time is I have gone ahead and drawn out some arrows. So we have a force of friction that is going to act along the plane, at least if there is one. We have a force of gravity that is acting down, and we have a normal force that is acting perpendicular to the plane. So I can go ahead and label those. Actually, that doesn't really look perfectly perpendicular to the plane. That's a little bit better. So we have the normal force, we have the friction force, and we have the force of gravity. The force of gravity, of course, is going to be mg. The force of friction is what we want to find. We don't know that just yet. And the normal force, well, right off the bat, we can say that it has some components. It has a vertical component, and it has a horizontal component. Then we can also say the same thing about the force of friction. It has a vertical and horizontal component. I think I might have gotten those mixed up a little bit. Yeah, it looks about right. And so if this is angle theta here, then we have angle theta here as well, and angle theta here as well. Those are all the same angle. Let's look at the normal force first. Notice that the dotted lines are the components of the forces. The solid lines are the forces themselves. Also keep in mind that the coordinate plane is not shifted. This is the x and y axis. So recall that with inclined plane forces, we will angle the coordinate plane to be something like that. We are not going to do that in this case. We're going to keep it in the same orientation. So here we have the normal force in the y direction. That, if you notice, is going to be equal to cosine of angle theta times the normal force. And then up here we have the normal force in the x direction, and that is going to equal sine theta times the normal force. Whatever the normal force is, it'll be sine theta times that. We can do something very similar with the friction force as well. Here, the friction force, okay, so we have the friction force acting along that solid line, and then here we have the friction force in the y direction. That's going to be equal to sine theta. Just look at your triangle here. It's going to be sine theta times the friction force. And then the friction force in the x direction will be equal to cosine theta times the friction force. All right, so once we've established those things, what we need to recognize is this, that the sum of forces, we know that the sum of forces, in fact, how if I switch to another color, hopefully this will be easy to see, the sum of forces in the y direction is going to be equal to 0. But we don't have only the normal force by the inclined plane acting up. In fact, what we have is we also have the friction force acting in the vertical direction as well. In fact, for a moment here, let's assume that there is no friction necessary, even just for a moment. If that were the case, okay, so if the friction force is equal to 0, then we can say that the sum of forces in the y direction would still be 0 no matter what, because this thing is not moving up or down the incline. And we're going to say that we have a negative force of gravity plus the normal force in the y direction. Those two, then you can see that they're equal to each other. And so we would say that mg would be equal to the cosine of angle theta times the normal force. I'm going to solve for the normal force here, and I'm going to say, let me extend my page a little bit. So I'm going to say that the normal force is equal to mg over cosine theta. And then I'm going to look at the amount of normal force that is acting in the direction towards the center of the circle. So that's going to be the sine of theta times normal force. So if I say that the force being caused towards the center of the circle, the centripetal force, or if you prefer the radial force, they are both the same thing. Let's use centripetal. The centripetal force is going to be equal to, as we said, the sine of theta times the normal force, because that is assuming that there's no friction. Okay, assuming that there's no friction, we would say that the force caused by the normal force in the x direction, that would be equal to the centripetal force if there is no friction. And so we can then take this and insert that into here. So let's go ahead and do that real quickly. So we'll say that the centripetal force will be equal to the sine of angle theta times mg over cosine theta, and you should notice that that is equal to tangent theta mg. Sorry, I ran out of room there. Let me just grab this and move it over. So tangent theta mg. All right, so if there's no friction force, then tan theta mg is going to be the force acting towards the center. That'll be the centripetal force. All right, now we can actually put a value to that. Plugging in the values of, let's see, we'll have tangent of 12 degrees times 1200 kilograms times 9.8 meters per second squared. Sorry about my writing. That would give us a value of, let's see, that would be 2,500 newtons. 2,500 newtons acting towards the center. This would be the normal force in the x direction, which can be the centripetal force. So that's basically the force available from the normal force. That's the force available from the normal force acting towards the center. All right, so now that I've looked at the available force available from the normal force acting in the centripetal direction, I'm now going to look at the amount of centripetal force needed for the car to run the curve from, just in general. So that's going to be the radial force or centripetal force, again, I'll use that, is going to be ma, but where a is equal to v squared over r. And so plugging in our values for that, we're going to say that this is equal to the 1,200 kilograms times v squared, which is the 26.39, that's meters per second squared. The units aren't squared. Well, they are eventually. Here, I'll write that in. Meters per second. And then that squared, it will square the meters and the seconds. And then that's going to be over r, which is, let's see, what did we say that was? Up here we said it's 67 meters. So 67 meter radius turn. And that is in turn going to give us a value of, let's see, it's going to be 1.247 times 10 to the 4th newtons. So 12,470 newtons roundabout. And so what does that mean? Well, that means that the force acting to the center, remember that we've got a value available from the normal force that is nearly 10 times less. It's actually, I don't think it's quite that. It was here. Let's see, what did, let me make it bigger so I can see it. So 2,500 newtons versus 12,000 newtons. 12,000 newtons are needed. Only 2,500 are available from the normal force. So that means that there is in fact a force of friction, and not only is there a force of friction, but it's actually acting towards the center of the circle. So that's how here I was able to determine that we have a force acting towards the center of the circle, because if this car was actually moving slow rather than fast, then there could actually be a force acting outwards due to friction. Because if you think about it, if this car is moving at a crawl pace, it would actually want to slide down the plane. So this has shown that our force is in fact acting towards the center, which is kind of needed for what we are going to do next. All right, so let's take a look at our diagram one more time. In fact, I should make this a little bit shorter, because what I've now learned is that if I were to take the force of gravity in addition to the force from friction, that in turn, oops, didn't mean to grab that, these should be equal and opposite. So let me make my force of gravity even smaller yet. Something somewhere along these lines. So what I'm saying is that the force of gravity and the friction force, the vertical part of the friction force, are both acting down, and those in turn are equal and opposite to the normal force, the vertical part of the normal force acting up. So let me put those back where they belong. And I'm now going to express that mathematically. So we're going to say that the sum of forces in the y direction, this is not if there's no friction, but this is everything. This is now everything combined. So we're going to say that the sum of forces in the y direction is equal to 0 newtons, which is in turn equal to the, let's say, negative force of gravity, because that's, we're going to say down is negative. Let me just say plus the normal force in the y direction and minus the friction force, which is in the y direction as well. So now substituting the things in there that we know, we're going to say that 0 is equal to negative mg plus the cosine of angle theta times the normal force minus the friction force. Oh, excuse me, that should be the friction force in the y direction. And so we're going to say that that is minus sine theta times the friction force. Let me add each side by sine theta times normal force, and then divide each side by cosine theta. I'll do that in one step here real quickly. And so I'll say that the normal force can be expressed as sine theta times the friction force plus mg, and that'll be all over cosine theta. Again, all I did is I just added sine theta to each side, and then then divided by cosine theta. So sine theta times the friction force plus mg over cosine theta is the normal force. All right, so what we can do now is we can look at the x direction. So remember where from the diagram in the x direction I have the force of friction in the x direction. I also have the normal force in the x direction. So sine theta times the normal force and cosine theta, the friction force. So let's go back down and express these things. So we're going to say that the sum of forces in the x direction is going to be equal to ma, as it always is. There is acceleration in the x direction. This is in the x direction. That is in turn equal to, let's see, we've got the normal force in the x direction plus the friction force in the x direction, and now I can go ahead and substitute those things in. In fact, not only that, I'm going to say that ma is actually equal to v squared over r. Its actual acceleration is v squared over r, and that'll be equal to sine theta times the normal force for the normal force in the x direction plus the force of friction in the x direction, which we said was cosine theta times the friction force. And moving along. All right, so I'm going to say that since the normal force, as we expressed from before, is equal to the sine theta times the friction force plus mg over cosine theta, I'm now going to substitute that in for the normal force here. So I'll put that in for that right there. So let me go ahead and do that. All right, I've gone ahead and written that out and moved things over so I have more room. And so notice that I've put everything over 1. It just makes it look a little bit neater and easier to see what's happening. So all I've done is I've just substituted in the sine theta, this part right here, I've just substituted in the sine theta times the force of friction plus mg over cosine theta. I've substituted that in for the normal force. Okay, and now what I can say is that I'm going to multiply each side by cosine theta. I'm trying to get the f alone, and so I'm going to multiply each side by cosine theta. So when I do that, let me go ahead and write what I'll have there. Okay, I did a couple of things real quick to speed things along. Firstly, I want to draw attention to this up here. I mistakenly had put in the normal force there. I should not have, so I just want to erase that real quick. And oh, yeah, that shouldn't happen. Okay, so I fixed that. And what I wind up getting when I multiply each side by cosine is I have mv squared cosine theta, because I multiplied each side by cosine theta, over r. That is equal to sine theta times, and in parentheses, I now have gotten rid of the cosine theta in the denominator here. And so it's just sine theta times the friction force plus mg. And then notice that here I have cosine squared. And actually, I didn't put in my theta. So there, I've fixed that. So, but do please notice that it is now cosine squared theta, because it is cosine theta times cosine theta. And you can notice that I'll be able to do the same thing here. So I'm going to distribute the sine theta through, and I'll do that real quick. So I've got mv squared cosine theta over r on the left, and I've got sine square theta times the friction force plus sine theta mg. So now I'm distributed through my parentheses, and plus cosine square theta times the friction force. Okay, again, all I need to do is I need to get the friction force alone, so I'm going to subtract each side by sine theta mg, and so when I do that, I will get this here. That's all I've done is subtract each side by sine theta mg, and you'll notice that what I've got here is sine squared theta times the friction force plus cosine squared theta times the friction force. And your trig functions, basically, since we can say that sine square theta plus cosine square theta is equal to 1, then basically that means that the entire right side of the equation is, in fact, simply equal to the friction force. So we can go ahead and just finalize and write that out. So the friction force is, in turn, equal to mv squared times cosine theta over r minus sine theta mg. So I went ahead and wrote out our values where m is 1,200 kilograms, v is 26.39 meters per second. Remember, it has to be in meters per second, and it is in fact squared. Don't forget that. That happens too common. Theta is 12 degrees, and the radius is 67 meters. So I've just plugged in those values, and then that will give us an end value of 9,755.8 newtons is what I've got. And if I'm not mistaken, if we want to do significant figures, if we go back to our original data, it looks like we have 2 sig figs, because we have 67, 1,200, and so on, 2 sig figs. So that will in turn bring us to 9.8 times 10 to the third newtons, and that's going to be down, acting down the plane. All right, so remember that without the force of friction, that you have the force acting towards the center equal to tangent theta mg, but since we have a force of friction here, we need to add that in with the force of gravity acting against the normal force, and we do also need to know, if you can see in green at the top here, we need this trig function to complete our work. All right, so hope that was helpful, and I'll see you guys next time.